Hi, I'm Alistair. I'm a games designer, and this is part of a series of videos where I'm looking at creating COVID-secure, touch-free interfaces for escape room puzzles or other Arduino projects. In this video, I'm going to be looking at an ultrasonic distance sensor like this one. Let me show you how it works. So this is an HC-SR04 module, which is one of the most common cheap ultrasonic sensors you'll find. You can see we've got a bunch of components on the back, and on the front we've got these two rather distinctive ultrasonic transducers. We've got this one on the left is labelled with a T, and this one on the right is an R. So rather like the infrared obstacle avoidance sensor we looked at in the last video, what we have here is a transmitter and a receiver. And the way that this unit works is that the transmitter broadcasts an ultrasonic wave in this direction, and the receiver listens to see whether it can detect that same ultrasonic signal being reflected back. If it does, that suggests that there is an object in the way of the sensor that the wave has bounced back off. If it doesn't detect anything, that suggests that the wave has just gone off into the distance somewhere and there's nothing in the way. Now, what's slightly different about this sensor compared to the infrared sensor is that because ultrasonic waves travel at a known speed, we can actually measure how long it takes for the signal to be reflected back and detected, and we can use that to estimate how far the object must be from the sensor. So let me show you that in action by plugging it into an Arduino. So you see we've got 4 pins here. We've got VCC, trigger, echo and ground, and I'm going to plug those into my 5-volt ground and digital pins 2 and 3. So you can think of the trigger and the echo pins as slightly like kind of an input and an output pin, for example. We'll use this one to tell the sensor to broadcast that wave, and we'll use the echo pin to measure how long until we receive the reflected signal back. And then as before, what I'm now going to do is I'm just going to hold that there while I turn on my Arduino serial monitor, and hopefully, so what I can show you is just as we had before, I can detect when an object is placed in the way. I can also detect when it's removed, and while it's being held there, what I'm actually going to do is to those series of numbers there actually show the distance in centimeters away the object is from the sensor. So as I move further away, those numbers get bigger, and then as I get closer, you'll see that they get smaller and smaller. Now, what you might also notice is that the signal is a little bit noisy. I'm kind of getting some false, like a bit like a mechanical switch bouncing there. It detects when my hand has been added correctly and when it's been removed, but while I'm holding it there, I'm sometimes getting kind of false extra positive signals there. So that's one of the things to note about this compared to the other sensors, is that the signal's a bit noisier. But it does have some advantages. The main advantage is that it is not affected by the type of object. So long as it's a solid object, it will reflect the ultrasonic wave. So I gave an example yesterday with this pen here. With the infrared example, only the light coloured end of the pen reflected the infrared light to be detected. But with an ultrasonic wave, any solid object will get reflected and detected again. So it doesn't matter what colour the object is, basically, so long as it's a solid object. It will also work at a much further distance. This unit will actually work up to a distance of about 4 meters before, and anything beyond that time, it basically takes too long for the signal to be reflected and detected again. But you can get a much longer distance. So here's a fritzing diagram just to illustrate the wiring in a slightly clearer way. So as you can see, I've got VCC on the sensor. That's connected to 5 volts on the Arduino through this red wire. We've got the two grounds connected together in this black wire here, and then we've got the trigger and the echo pins on the sensor. And like I say, you can think of these as a bit like the data input and output lines. So the Arduino sends a message to the sensor on the trigger line, telling it to broadcast an ultrasonic wave, and then it listens to a response on the echo pin. So I've got these connected to digital pins 2 and 3, but you can use any spare GPIO pins on your Arduino. It's just a matter of adjusting the code to let the library know which pins to use for those functions. So here we've got the code that's running on the Arduino. It's not too long and it's not too complicated, so we'll simply step through it line by line. And the first thing we do at the top of the code is we include this external library called Ultrasonic. Now, this is a package of generic code that's already been written that's going to sort of wrap up the functionality of the ultrasonic sensor and just make it more convenient to use. So the process of triggering an ultrasonic wave and then waiting to see if it gets reflected, and if it is detected, again, calculating the length of time it took to receive the reflected signal, and then converting that into a kind of a useful unit of measure. All those kind of functions have been already written and are already available in this library here. So rather than kind of starting from scratch, we'll make use of this library to provide that in our code ready-made. Then we go on to the constant section. So the constants are variables which are not going to change over the duration of this code. The first one, so this is the pin that we have got an LED attached to. I'm using pin 13, which on most Arduinos already has a built-in LED on the board wired to that pin there. So by setting this to be high when an object is detected, it's going to make the LED light up. And if an object is removed, this pin will have a low signal written to it, and that will turn the LED off again. But you could wire anything you wanted to this pin. This could be a relay, for example, that triggers some external load, or you could assign a different pin to it if you wanted. I'm using the LED pin because remember that the ultrasonic sensor board itself did not have any kind of visual output. It doesn't have an LED on the board or anything to indicate whether it's working or not. So this is going to give us some useful visual feedback to enable us to test the code. Now, the next constant we have here, so this is a constant called max distance, and I'm going to set that to 100. Now, this needs a little bit of explanation. So the sensor itself is capable of detecting objects up to a maximum distance of 400 centimeters or 4 meters away. But we're not actually going to use that full detection range. We're going to set the detection range to a lower value than that. And there's two reasons for that. The first one is because we don't want the sensor to accidentally get triggered just because someone has walked past in the background or there's some kind of movement which we don't want to listen to. We're trying to simulate a kind of a deliberate user input here. So we want to have kind of a fairly narrow range within which they have moved their hand or body or placed an object or something like that to know that it was a deliberate intentional action to trigger the sensor. So I've set it to a value of 100 here. This is 1 meter, but actually you could set that to 50 centimeters or 20 centimeters, however far away you wanted. And by setting this to a lower value, that's going to make your user input kind of more specific and a deliberately intended action. So that's the first reason, but there's also a second reason for setting that to a low value, and that relates to this third constant here, this timeout value. So remember the way that this sensor works is that we trigger an ultrasound signal and then we wait to hear whether we receive that signal get reflected back to the sensor again. And let's suppose that we were setting a maximum detection range of 400 centimetres, so 4 metres away. If that were the case, we would have to wait after every signal for the length of time potentially for that wave to be bounced back 4 metres to get to the object and then 4 metres back again and then for it to be processed. So actually it would take quite a long time in between each time we could trigger a new signal. We'd have to wait until we could set the next one out again, because we can't send the next ultrawave sound until we've waited for the first one to be received each time. And the farther the distance that we're potentially trying to detect objects in, the longer we have to wait to see if that gets reflected or not. So by setting the maximum detection distance to a lower value, it also means we have to wait less time to decide, actually no, this signal is not going to get reflected. There obviously isn't an object within this range, so therefore we can send the next trigger out. And we'll find that the functionality and the code actually becomes more responsive because we have to wait less time in between each trigger that we send. And that amount of time that we actually have to wait, we can calculate using this formula here. So it's the maximum distance of the object away that we want to detect, and then we multiply that by 58. Now I'm not going to go into the details of how that number was calculated, but I can explain briefly. It's because the ultrasound signal obviously needs to be sent first of all, then we have to wait for it to be reflected, so that's twice the distance. And then if you take account for the speed of sound in air as well and multiply that together, and the fact that this is measured in microseconds, and whereas this is measured in centimetres, when you take all those into account you end up with this magic number 58, and that's going to give us the length of time we're going to wait in between each signal based on the maximum distance that we want to detect objects in. So that's all our constants. Then we get onto the globals. So globals are variables which are shared between all of the sections of code we're using here. And so we define an ultrasonic object here. So this is something that's defined by that ultrasonic library which we included at the top of the code here. And we create a new ultrasonic object on the specified pins that we plugged the trigger and the echo pin into on our board, and also the length of time that we calculated up here. So that creates our new ultrasonic object. And we also use this flag called detected. And if you saw my last video where we used the infrared obstacle avoidance sensor, this works in exactly the same way. This is just a Boolean flag that we're going to use to tell the difference between a new object that's been detected by the sensor, or whether an object has been held in front of the sensor, so it was previously detected and it's still there, or whether an object that used to be detected has now been removed. So that's what we're going to use that flag to keep track of. So we enter the setup function. So this is what's called when the code first starts running. We create a serial connection. We dump to the serial output the name of this script and the date when it was last compiled. That's just useful bookkeeping information. And we also configure that LED pin which we're going to use as an output. Again, like I say, you don't have to have an LED connected to that. You can have anything you want. But if you're using pin 13, as I am, that's going to make an LED light up when an object is detected. So it's kind of convenient. Then we have our 3 functions which are going to be called based on the 3 possible states which the sensor detects. The first one is when a new object is detected that wasn't there previously, and when that happens we light the LED up, we write a message to the serial monitor, and we set our detected variable to be true. Or it might be that we are detecting an object in this frame and we already knew that there was an object in the last frame as well, so in that case it's being held. Now, in a slight variation from the infrared obstacle sensor example, in that one I simply printed a line of dots which got longer and longer the greater amount of time that an object was held in front of the sensor. Here, because we actually get a reading of how far the object is, we're going to print the distance in centimetres. So potentially you could use this as the basis for a sensor of not just whether an object is being held, but is it moving closer to the sensor, or is it getting farther away, or is it being held at a particular range of distances away from the sensor, for example. You could use that as a puzzle here. And then we've got input removed. So this is called when there had been an object in front of the sensor last frame, but now it's been taken away. And when that happens, we turn the LED off, we tell the serial monitor to print a message that it's been removed, and we set our detected flag back to false, so that next time an object is detected, we know it's a new object rather than just the same one being held there. And then we enter our loop. So this is our main program loop that just runs over and over while the Arduino is powered up. And on each frame, what we do is we call this ultrasonic.read function. So again, this is a method that's provided by that ultrasonic library we included here. We then created our object from that library here, and we told it what pins it was connected to. So it just means that very conveniently we can now call this read function, and that will tell us if an object's been detected, and if so, what the distance away it is. So we don't have to do any of that calculation ourselves. But what we will do is we will now write the logic as to what we want to do based on that value. So we've got raw reading here from the sensor. If that's greater than 0, that's a good thing. It means that we are detecting something and it is at a given distance away from the sensor. And we also, remember, we only want to detect objects that are less than the maximum distance away. So a combination of these two conditions here lets us know that the reading is somewhere between 0 and the max distance, so an object has been detected. If that's true and detected is false, that means that either this is the very first object that's been detected, because remember when we declared detected up here, we initialized it with the value false. So the very first time the code runs, that's going to be false. Or every time the last object was removed, it's set back to false as well. So if this bit gets run here, it means that an object is being detected in the correct range, and we didn't know about anything before. Therefore, we'll call the input detected function, which we had up here. Otherwise, so this section here gets called when there is an object that's detected, but detected is not false. So detected was true, we knew about this object already, and in that case we'll call the input held function, and we'll tell it what the current distance being detected is. Now if this statement here is not true, that's when we enter this else statement here. So this means that either raw reading was outside of the maximum distance we were allowed to be detected, or perhaps it was 0 or a minus number, or for whatever reason it wasn't a valid value. So there isn't an object that's been detected. We'll enter here. If there was one previously though, so we previously knew about an object that was in range, now we're not getting data about that anymore, so that means that it's been removed, and we will call the input removed function instead. And then we'll just insert this slight delay, so this just slows down the code so it's not trying to run absolutely as fast as the Arduino is capable of. It's also always a good idea to give the ultrasonic sensor a little bit of a delay before sending the next one as well, just to make sure that it doesn't pick up any kind of echoes from the previous signal or anything like that. So it kind of clears everything out, and we'll start again next frame and do it all again and just loop around forever. So rather like the infrared sensor we looked at last video, these units are very easy to use, they're very cheap. And the advantage they have over the infrared sensor is that they're able to detect objects from a further distance, anything up to 4 meters. And also they're able to give an indication of the distance from the sensor as well. The disadvantage they have though, as you will have seen in the demonstration, is that that signal can be a little bit noisy. And if what you're looking for is a replacement for a mechanical button, I'm not sure that this necessarily would be the best choice. In the next video, we're going to be looking at another type of sensor again. First we looked at infrared, then ultrasonic. Next time we're going to be looking at a laser time of flight sensor, and we'll compare the advantages and disadvantages that offers. I hope you'll join me for that one.